In the last part, we have seen a discrepancy between theoretical shear strength and experimentally observed shear strength. And we found that theoretical shear strength was higher than experimentally observed shear strength. And we reasoned that for a breaking and making of bonds. So we came up with a thought of process of dislocation where locally there is already broken bonds available. And thus we don't have to use too much energy to make and form bonds and so as to cause a deformation. So we have seen this scenario in the last part, and we have seen when shear stress applied, you have the plastic deformation accommodated by a displacement vector, and this displacement vector now we call it as, in terms of dislocation, as a Burgess vector. So this displacement vector which accommodates this plastic deformation or shape change is called as Burgess vector. Now if you look at these two crystal structures carefully, here you have a kind of a perfect crystal structure or a lattice, a perfect lattice over here. However, if you look at this, here you can say that the lattice is not perfect, or there is locally there is a bonds which are broken here in this case, or I can say that here I have put an extra half plane. How I am saying this? That because we are seeing this in 2D, and if you extend that, there are atoms in 3D. So let me do that. So these atomic planes are extending it in the third direction, and that is why when I say extra half plane, that is this plane. So this is an extra half plane which can be seen as an inserted in this a perfect lattice, and that's what makes it a defective lattice. So this is an extra half plane. So I call this as an extra half plane, or this extra half plane can be visualized here using a hard sphere model. You can see here the hard sphere model, and you can see that this is an extra half plane. You can clearly see that if I join these atoms together, this will be an extra half plane which is inserted in a perfect lattice. Similarly, here you can see there is an extra half plane here inserted. So this is a typical of an edge dislocation. We'll define it mathematically also, what is an edge dislocation. But now here you see that this extra half plane is peculiar to this kind of defect. And if you see this line, or this is a plane of atoms over which there was a glide happening. So when we saw that if I put a shear stress, this upper part of this crystal will glide over this plane and cause a displacement vector. We have termed it as Burgess vector. So this plane of atom, here also I am marking this plane of atoms, is called as a slip plane or a glide plane. Now let me define what is slip plane or a glide plane. The plane of atoms or a plane on which slip occurs or a dislocation glides. I am calling this now a dislocation. We will define it what it is, but the plane on which this dislocation glides or moves or slip is called as a slip plane or a glide plane. So we have got introduced to three terminologies. One is Burgess vector, which quantifies a displacement vector or which quantifies a deformation. We have got introduced to an extra half plane, by which after inserting I can see that the perfect crystal was made into a defective crystal. So this extra half plane I have inserted, or I can say that I have removed an extra half plane from the bottom. This is also I can tell. So another thing what I can say that the extra half plane is added or extra half plane is missing when I am talking about a dislocation. Here we can clearly see that if I insert this plane, extra half plane here, I can make this into a perfect lattice. Or if I am taking this out, I can make it as a defective. Or in other words, I can insert the extra half plane and make it defective. So extra half plane is a peculiar for this dislocation. I have marked these sleep planes over here in the structures also. So these are sleep planes over here. Now let us look at something over here. So I can see that there was atoms were missing, a line of atoms were missing inside. Here also I can see that there is a line of atoms missing, and that line I'm call it as a dislocation line. And let us visualize it, how it is. So here we know this is an extra half plane, and this is our sleep plane, which is green and yellow, and red is extra half plane which I have inserted, and this is a displacement vector which is a Burgess vector, or it is called as a sleep vector too. So we have sleep plane which we have seen, or this is also called as a glide plane, and we have an extra half plane over here. Now where is the dislocation line? If you see that just below this line which is representing, let me write it down. So this line which I am talking about is a dislocation line. Let me mark it. So this line just above, this is a dislocation line. So this is a line, that is why this defect is called as a 1D defect or a line defect. Now let's go and understand this defect in detail. So this dislocation, that is, I term it as now as an edge dislocation, has a unit tangent vector along a dislocation line, that is T, and B, which is a Burgess vector. With these two vectors, we are defining a dislocation, that is a line defect. Now, if you look at this crystal, I have marked this sleep plane, and this green is an extra half plane. Now let us mark this sleep plane over here, and let us mark this extra half plane. This line is called as a dislocation line, and this is represented by a vector called vector T, which is nothing but a tangent vector along the dislocation line. So this is a dislocation line, and this is a vector which is a unit vector along this dislocation line called as a tangent vector, and this gives the direction of the dislocation line vector. And we have a Burgess vector which is I have marked in this fashion. So this is denoted by B, and this gives the direction of the Burgess vector or a displacement vector. So B identifies what is a displacement vector. And one more important point, this dislocation line demarcates that what is slipped region and what is unslipped region. This is very important. So dislocation line demarcates. So when this dislocation moves or glide on this slip plane, this demarcates a slipped region and unslipped region. Another important point for a edge dislocation, that this slip plane, you can see that this slip plane contains these two vectors, that is a T vector, that is nothing but a unit tangent vector along the dislocation line, and Burgess vector. So slip plane for an edge dislocation always contain a T vector and Burgess vector. This is very important point to note. Now let's go and understand this edge dislocation in more detail mathematically also. So this is a cartoon which I would like to play. So you can see that there is locally bond is breaking and making. You can see here in this cartoon that the dislocation line is moving. This dislocation line is moving on this slip plane, and the bonds are locally making and breaking. So you can see that there is a creation of step when this dislocation moves from one end to another end, and this step is marked by a Burgess vector. So you can see clearly that the dislocation is gliding on this slip plane, and the dislocation line is into this plane of this surface or this screen. So you can see the movement of this dislocation line on this slip plane, and this you can clearly identify as an extra hub plane. Now let us go and see the schematic over here, where I can see that this is an extra hub plane, this is a slip plane, and here there is a dislocation line. So I have an extra hub plane and I have a slip plane, and here is a dislocation line. So let me draw a schematic here. I am now looking from the top. How I will see that this is a slip plane, and let me mark the dislocation line vector now. So this is a dislocation line vector which is marked green cross, which is going into the screen. So this I am seeing as a dislocation line vector, and I have marked a direction also. Now if you see or carefully in this cartoon, that when the dislocation is moving, this Burgess vector is perpendicular to the dislocation line. So you can see that the Burgess vector is perpendicular to the dislocation line. So dislocation line is going into, that is this cross I am saying, is going into the surface or this screen, and the Burgess vector is perpendicular. So Burgess vector is moving, let me write it down that. So Burgess vector is moving in this direction. This is the Burgess vector, and a dislocation line is inside. So this is our T, which is into the screen. So let me mark Burgess vector here, where Burgess vector is perpendicular to a dislocation line, and this we call it as an edge dislocation. So this kind of defect is called as an edge dislocation, where the Burgess vector is perpendicular to a dislocation line vector. This is a definition of an edge dislocation. Now this is a slip part. So when I say that half plane is over here, so this region is already slipped. You can see here. So the slip starts from here, and this will be a slipped region, and this will be a unslipped region. So I can mark based on my half plane which is a slip plane or slipped region or unslipped region. So basically a dislocation line, that is this dislocation line, demarcates between a slip region and unslipped region. So this is an unslipped region, and this is a slip region. So let us mark here. So this dislocation line signifies or identifies which is a slip region, slip part of the crystal, and unslipped part of the crystal. So here you can see that the slip is occurring at this region, and this will be, and the slip will be progressing in this fashion. So when I pause somewhere here like this will be a slip region, and this will be an unslipped region. So another important point you should note is that the dislocation line vector demarcates between slip region and unslipped region. Now let us reiterate what is an edge dislocation. So edge dislocation is a line defect where the Burgess vector is perpendicular to a dislocation line. So this is a definition of an edge dislocation. Now there are some important points that has to be noted, that when edge dislocation moves, the direction of dislocation moment is perpendicular to the dislocation line. So we can see that the dislocation is moving in this way, and you have a dislocation line here. So the direction of dislocation moment is perpendicular to the dislocation line. So this is what we can see, that this movement is perpendicular to this T vector. Another important observation, the direction of dislocation moment is in the direction of stress. So when I can say that when I apply a shear stress in this fashion, this dislocation line will move from slipped region to unslipped region. So we have, let me mark it here. So we have shear stresses acting like this. So the dislocation line, this movement of this dislocation line will be in this fashion only. The dislocation movement, that is dislocation line, is in the direction of stress. Now let us look at some interesting points about edge dislocation. Is that this is an extra half plane which I have put here. This is on the top side of this crystal, and I can insert the half plane from the bottom also. So here I can say that I have inserted an extra half plane, or I have removed an extra half plane from the bottom, or here I can say that I have inserted an extra half plane at the bottom, or removed an extra half plane from the top. So this kind of two scenarios can be possible. So in three-dimensional symbol, what you can write is that you mark this as a dislocation line. Let me write it down. So this is your dislocation line, and you mark a Burgess vector over here. And in 2D, you can see this as this symbol. So let me write it down. So you can see this as an extra half plane and a slip plane. So your symbol, 2D symbol, is inverted T. That is for this type of dislocation where extra half plane is at above. Now similarly, I can put this 3D symbol for this scenario where the extra half plane is the bottom. I have this dislocation line vector, and this is a Burgess vector. And this dislocation is called as a positive dislocation, and this dislocation is called as a negative dislocation, and it is represented by inverted T. So this represents a slip plane, and this is the extra half plane is inserted at the bottom. So this is the two dislocations, that is positive edge dislocation and negative edge dislocation, based on the location of extra half plane. Now mathematically, how will you define it as with respect to, because we have defined edge dislocation with respect to B and T, that is Burgess vector and a dislocation line vector. So mathematically we define T cross B. If T cross B directs towards extra half plane, let's say T cross B is in upside, let's say, let me write it down. So T cross B directs or gives up direction, or this direction, this is called as a positive edge dislocation. If T cross B, the vector product, comes out to be negative side, so that is called as a negative edge dislocation. This is how you define with mathematically edge dislocation, positive edge dislocation and negative edge dislocation. And these are the symbols which you find in 2D case, that is inverted T for a positive edge dislocation and T for a negative edge dislocation. And these are 3D symbols. Now let's move ahead and see some other dislocations. So before that, let me introduce to a term called as Volterra cut. So this kind of a cut made into continuum solids by Vito Volterra, and he did it in 1907. That is way before dislocations were thought. So if you remember, in last part we have said that the dislocations were thought in 1934, and this was done by Volterra, that he made that there may be a dislocations or a defect in a continuum solids. And what he did, so he took a solid like this and he made a cut, that this square cut which is marked over here in a red, and he said this as a tangent vector. Let me write it down. So this is a tangent vector, and now what you can do is that I have made this cut, I can push this material, top material, with respect to a bottom material in this fashion, or let me write it down, let me change color too. So I can push this material in this fashion or in this fashion. So let's do that. When I push my material in this direction, that is perpendicular to this T vector, I form an edge dislocation. Here you can see clearly the symbol of edge dislocation which is coming out. So where you can say that the Burgess vector is perpendicular to tangent vector. So this is what is a definition of an edge dislocation. Burgess vector is perpendicular to a dislocation line or a tangent vector. Similarly, what I can do is that I can have, if I push this material in this fashion, I create a defect in this continuum solid, and here you can see that the Burgess vector is parallel to T vector, and this kind of defect is called a screw dislocation. So we have seen a definition of an edge dislocation, which is Burgess vector is perpendicular to a tangent vector. Now we are getting introduced to another type of line defect, which is a screw dislocation, and which is defined as Burgess vector is parallel to tangent vector. You can see clearly here. Let me show it to you. This was our T vector, and this is our Burgess vector in this fashion. So you can see that this Burgess vector is parallel to a tangent vector in case of a screw dislocation. Now how this cut has been made, so we have a perfect crystal and you choose a plane of your interest and you shift material. Now I am shifting this material in this fashion. So I have a dislocation line which was, let me write it down. So this was our dislocation line here which will be created. So which is going into the picture. So when I push this material, what you can see that you have a Burgess vector or a displacement vector is perpendicular to the dislocation line, and this kind of arrangement which we get is an edge dislocation where Burgess vector is perpendicular to the dislocation line. Now let's look at the scenario for a screw dislocation. I take a perfect crystal, I mark a cut over here, and that cut is made through Volterra knife. Okay, so and then what I do is that I push this material along the dislocation line. So your dislocation line and Burgess vector are parallel to each other, and you create a defect like this. This is called as a screw dislocation. So these are two important definitions now for a dislocation. So when Burgess vector is perpendicular to dislocation line vector, it is called as an edge dislocation. Where Burgess vector is parallel to the dislocation line, it is called a screw dislocation. Now let's look at screw dislocation in more detail. So we have defined screw dislocation as Burgess vector parallel to the dislocation line vector, that is T vector or a tangent vector. So we can see here that you have a dislocation line which is going into the crystal, and the Burgess vector is parallel to the dislocation line. So you can see that what I have done, I have a perfect crystal and have twisted this crystal in a fashion. Let me write it down. So I have pulled this crystal or sheared this crystal in this way. So you can see that the top part has moved or sheared with respect to a bottom part, and it creates a step which is marked by a displacement vector known as Burgess vector. And this Burgess vector, you can see clearly, it is parallel to a dislocation line. Now let's visualize this screw dislocation. As you are getting introduced for the first time to this screw dislocation, you must understand how it looks like. So these are heart sphere model which I have shown, and you can see clearly that you have a defect. So let me mark it over here. Let me write it down. So I have this plane where I am moving in this way, so I don't have any defect. But when I spiral down, let me change the color. When I spiral down, let me go here, move in this way, and when I see that I have landed up in a top above atomic layer. So this is one layer and this will be another layer. So I have landed up in another layer just by moving around. So here you can see clearly, if I start like this from bottom plane, I will move in a helical way, I will come like this and will end up at this top atomic layer. So here this line which is going through and through the crystal is a dislocation line here. Let us mark that. So this is our dislocation line. So this is our dislocation line which I have marked with a green color. So this transparent green is showing that the dislocation line is inside the crystal. So here also let me mark. So this is going through this region and coming out from the other side. So this is the dislocation line. Now let me show you how we are moving. So if I am moving on this plane, let's say with this blue arrow, and I go here, again I traverse in this direction, again I traverse this way, again I try to come back. So you can see there is a step which is being created. If this would have been a perfect crystal, I should have come to a same position if I am traveling the same distance. Let's say east, west, north, south. If I start traveling the same distance, I should come back to the same position. But now what is happening that I am a one layer above, and this displacement vector which I am seeing is parallel to the dislocation line. So that is very important. So I am moving in this way and I am coming up by a displacement vector parallel to the dislocation line. So this is called as a screw dislocation. I'm moving as a screw and ending coming up or landing up in a top atomic layer. So let us mark this screw dislocation and try to understand mathematically. So this is our slip plane and I have a tangent vector which is marked in this way, which is nothing but representing my dislocation line. And this is our Burgess vector. So you can see here from this scenario, this will be our slipped region. You can see that this region is slipped region and this will be unslipped region. So this is the dislocation line bifurcates between slip region and unslipped region. This we have seen in case of an edge dislocation also. So when someone asks you what is screw dislocation, you have to define that the Burgess vector is parallel to the dislocation line. Now, as we have seen, there are two types of edge dislocation, that is positive edge dislocation, negative edge dislocation. Similarly, based on what type of screw or the helical way you follow, will identify it as two types of screw dislocation. So that is called as a right hand screw, and in the 2D symbol will be like this. So we are moving in a clockwise way and the dislocation lies is into this surface or this screen, while left-handed screw will be in a counterclockwise way and this dislocation line is represented by a dot which is into the screen. So these are the two symbols for right hand screw and left hand screw. Now how they are mathematically represented? So when B dot T becomes equal to B, because T is a unit vector. So if the magnitude is positive, that is called as a right hand screw. This is by convention. And when B dot T is negative B, that is a left hand screw. So basically you can identify whether right hand screw or left hand screw. You take a dot product B dot T and then find out whether if it is B, it is right hand screw dislocation, and if it is a negative, it is a left hand screw. So this is why our convention. One more important point I would like to tell you is that 3D symbol is represented in this fashion, where you mark this S or a dollar symbol and you put a Burgess vector along this dislocation line vector. This is a 3D symbol. Now let's look at screw dislocation in more detail. So let's visualize it, how the screw dislocation is exactly. So here there is a picture which I have shown. Let me mark something on this picture. So when I say that it is a screw dislocation, you can see that if let us consider this as an atomic arrangements. These all are atomic arrangement. This each dot here is represent an atom. Now the arrangement of screw dislocation is in this fashion. So if I am on this plane, so I am traversing like this, I will end up and then again come back from here and again come back here. So this is kind of a helical path which we follow, and this is what the arrangement of atoms around the dislocation line. So let me mark that dislocation line also. So the dislocation line is this, which is marking this defect in the crystal. So this is our dislocation line, which is, we call it by a T vector. This is how we can visualize a screw dislocation. And the displacement from a top position to bottom position. So let me mark that also. This displacement is given by a Burgess vector. Now let's see how the dislocation or the screw dislocation moves. Or we have seen the cartoon for an edge dislocation. Now let's look at a schematic for a screw dislocation, how the screw dislocation moves. So this is our perfect crystal, and let me write it down. So this is our dislocation line. This is our dislocation line, and this is a slipped region, and this is unslipped region. So this dislocation line demarcates between slipped region and unslipped region. And let me mark a Burgess vector, which is this in this direction. This is a Burgess vector, and you can see that as I shear this crystal, the dislocation line is moving towards left. Let me mark that also. So this dislocation line is moving towards left. You can see that the dislocation line is moving towards left, and once this dislocation line reaches extreme, there is a step which is created. You can see here there is an offset which is being created. This is an offset which is being created. Let me mark it here. So this is an offset created by a displacement vector and is quantified by B. And there are certain points to be noted here, that when a screw dislocation moves, the direction of dislocation movement is parallel to the dislocation or dislocation line. So you can see that this Burgess vector is traversing parallel to the dislocation line. And the second point is the direction of dislocation movement, that is a dislocation line. So this is a dislocation line. The direction of dislocation movement is perpendicular to the direction of stress. So we have applied stress in this fashion, and the dislocation is moving in this fashion. Or you can see that I have marked over here. Let me write it down. So shear stress is in this direction, that is tau, and the dislocation line is moving in this way, T movement. So you can see that the movement of a dislocation line is perpendicular to the direction of stress. So with this, I'm stopping here. We have seen what is screw dislocation and what is an edge dislocation. We have identified their different types. We have seen how mathematically express them, and in the next part we'll be going to see more of dislocations.